So today is all about resolving vectors into x and y components. Now that's a big title, and we'll see in a minute that you can reword that in a way that's a little bit easier to understand. But that's what we're after, so we'll start with that. But before we talk about vectors, I just want to talk about a bowl of fruit. And here's the bowl of fruit, and in this bowl of fruit, I'm going to put a little apple, and maybe another apple sort of here, a little smaller apple, third apple. The apples get smaller as you go, I guess. And then here I'm going to put a little banana in there, and then maybe there'll be another banana sticking out over here, and then a third banana tucked in this way behind there, and a fourth banana sitting over here. So all together, we have a bowl with 7 fruit. Not so hard to understand. Okay? If we were describing this bowl of fruit, we could tell people I have a bowl with 7 fruit in it. But perhaps there's a way we could give them more information. We could also describe the number 7, the 7 fruit, as 3 apples plus 4 bananas. So in a sense, what we're saying is 3 plus 4 is 7. That's 2 different ways of saying 7 fruit, but one way gives us only the number of fruit. The other way tells us more stuff, useful information, right? So 3 plus 4 could be used, or 7 could be used to describe this bowl of fruit. And if I use 3 plus 4, well, I have a good reason, because it tells me about the apples and the bananas. Now, in math, I could write lots of ways to get 7. I could say 2 plus 5 is 7. And that's a true statement. But according to my bowl of fruit, that has no meaning. It doesn't help me. It's useless. I could say 1 plus 6 is 7. And that's true too, but that is no information that's useful. I could go 4.3 plus 2.7 equals 7. But why would I? In fact, I could go on forever finding 2 numbers if I use lots of decimals that would add up to 7. And none of those would matter. I wouldn't care about any of them, except for this one. This one has special meaning because not only does it add up to 7, but it tells me the number of apples and bananas, which I might want to know. So it turns out that sometimes a number can be expressed as the sum of 2 other numbers that are useful and meaningful, even though it's just the same number. So I want you to think about that concept, which I'm now going to apply to a vector. And this is where it'll look a little bit more complicated. So what I'm going to do is I'm going to draw a typical vector. So I'll make a little axis, and I'll draw this vector right here. I'm going to say he's 10. Doesn't matter what the unit is. Could be displacement, could be velocity. And I'll also tell you his angle. His angle is going to be 60 degrees. So I'm going to just draw that vector here in a couple different places because I'm going to use them. But it's the same vector, 10, 60 degrees. And we'll even go down a bit. There we go. Let me clean that up. Okay, I'll draw them down here. 10, 60 degrees. Now, just like 3 plus 4 was 7, I can do the same thing with vectors, except adding with vectors is a little more complicated, isn't it? It's that tip-to-tail thing. And if you add 2 vectors, for instance, if I start on the first picture, I pick vector number 1, or vector A. As long as I start here, if I go like this and make a line, and there's my vector A, then I can make another one that's tip-to-tail, and as long as it points over here, call that vector B. And the statement I can write is that the vector 10 at 60 degrees, because it's a vector, so it has to have a direction with it, is equal to vector A, whatever that is, plus vector B. That's the same as 7 equals 3 plus 4, but it's in vector language instead of actual math language, counting language. It's still math, but it's not counting, it's not scalar numbers. But just like before, where I could go 2 plus 5 for 7 and all those other ways, I can do the same with vectors. Here I'll do another one in a different color. I could go this way, call that vector C. It's a different one. And as long as it's tip to tail, see how it's tip to tail here? And it ends in the right spot and starts in the right spot. If this is vector D, I could also say that the vector 10 at 60 degrees, which is the black one, is also equal to C plus D. And I could keep going on this trick. Let's go purple, and I could go, I could make a line that goes way over here like that, call that vector E, and I could go make another line. They're tip to tail, and they start and end in the right spots, so I could say that the vector 10 at 60 degrees is also equal to vector E plus F, just like with the bowl of fruit. Except none of these are useful. Why would I do this? It's like 7 equals 4 plus 3 plus 2.7. Who cares? It tells me nothing about the fruit, and these vectors don't seem to tell me much of anything either. However, there is one particular sum of vectors that will tell me something very useful, and I'm going to draw that one next, because it's the one we want to work on. It is our 3 plus 4. That means something. So let me draw another line here. And let me draw the very same vector that we had before, 10. I'll draw it a little bigger so that I can write on it, and 60 degrees. There's one particular set of arrows or vectors that I could draw. I'm going to draw them in red. If I start here and I draw exactly along the x-axis, straight out, and I stop right underneath the end there, so that the next tip-to-tail vector will go straight up and down, which effectively is on the y-axis, so that it's 90 degrees, these two particular red vectors actually will have a very important meaning. I'm going to call this one, because I drew it on the x-axis, I'll call it little vector x right now. And because this one's on the y, I'll call him little vector y. But the vector 10 at 60 degrees is equal to vector x plus vector y, because they are tip to tail. They're just one of the many combinations that would have worked. Now we're going to find out why they're important and why they matter. Okay? I want you to think about a triangle here. And first of all, let's try to figure out a little bit more about Mr. Y and Mr. X. Well, vector y right here can be thought of as the y component of the vector 10 at 60 degrees. The y component. Or another way of saying that is the vertical component. Component just means the part. The vertical component of the vector of 10 at 60 degrees. If you want, though, you can think of it in simpler language as just, it's the uppy-downy part. Uppy-downy. It's the uppy-downy part of this vector, 10 at 60 degrees. But it all means the same thing. Now let's look at the other side, which is the X guy. I'm going to draw him in blue over here so that we can get him a different color. If I do this guy, he would be called the X component of this vector 10 at 60 degrees. Or we could also call him the horizontal component. That's another word, horizontal component of this vector. Those are two words that mean the same thing. Or guess what? We could call them the lefty-righty part. Lefty-righty. How much of this vector is lefty-righty? So that's what we'll call them. Trick now is to figure out if we can figure out how long they are, how much are they worth, do they have a number associated with them. So now that we know what they're called, let's see if we can get a number to go with them. Let's draw the vector one more time. 10, 60 degrees. I'll draw, in blue I'll draw Mr. X right here. There he is, X. And in red I'll draw Mr. Y so we can see them separately. Now, if I recall my mathematics, somebody once told me that sine theta is equal to opposite divided by hypotenuse. Correct? If I multiply both sides of this little equation by hypotenuse, this is what I will end up with. Hypotenuse times the sine of theta will equal opposite. If I look at my little angle 60 degrees right here, the opposite side of that is y. So y is the opposite. So this becomes y. The hypotenuse is 10 and the angle is 60 degrees. So the y part, the y component of this vector, is equal to 10 sine 60, which I can figure out, because the sine of 60 happens to be about 0.87 if you round it off. So this times 10 would be 8.7 equals y. By the same token, the cosine of theta is equal to adjacent, over hypotenuse. So, if I multiply both sides by hypotenuse, I get hypotenuse times the cosine of theta equals adjacent. Which means, if I go back to my picture, there's my 60 degrees again in the green circle. Right here, the adjacent side is x. X is beside the angle, right? And so therefore, the adjacent is x, but the hypotenuse is still 10, and I would get cosine 60 degrees, and that happens to be 0.5. So times 10 would be 5. So now I have numbers. So what this is telling me is that the black vector, the 10 at 60 degrees, is the same as going sideways 8.7, sideways 5, sideways is x on this one, and then going up at the same time 8.7, as if you had an Etch-a-Sketch and you were turning your two knobs. You turn the sideways knob 5, you turn the other knob 8.7, and you will trace the line 10 at 60 degrees. All right? And that's basically how we can figure out what the components are for each of these vectors. And these are called the x and y components. And this process is the title. What we have done is we have resolving a vector into its x and y components. And it's very important to know how much is uppy-downy and how much is lefty-righty, because all of our reference frames are built on that. And then we will be able to look at these, and we'll be able to pull apart questions by looking at the components of these vectors. Okay, let's do a couple of examples. Let's just work a couple of examples out here. See if you can figure out how to do them. So I'll give you 3 random vectors here. First one will make it easy. Call that 80 degrees. And then I'll give you this one. Let's put him down here. And let's put this at 30 degrees. And we'll do one more over here in the corner. And we'll put him down this way. And we'll say that this angle is 70 degrees. What I want you to do is draw in their components. Remember, they have to be on the x and y axis, so they have to be right angles and straight up and down and left and right. And then I want you to try to figure out how much they would be. Now I have to tell you, of course, the length of these lines. Let's call this guy 20. Let's call this guy 100. And let's call this guy, 40, just for fun. So go ahead and try and do that. I'm going to pause while you do that, and we'll come back and take them up together. Okay, we're back in what seems like no time at all. And through the magic of computers, I have rearranged the order of these so they're a little bit easier to write. So they look different all of a sudden now if you're watching the video because I just moved them around, but they're all the same question. So let's do this first one. I'm going to draw my x over this way, but I have to stop right underneath it. I can't go too far, or not far enough. This has to be 90 degrees. Now notice that I could also have gone this way. And I would have got exactly the same arrows. But because I don't have the 80, I'd have to do the extra step of subtracting 90 and getting 10 degrees here. So that's extra work. So it makes more sense when you're doing this to just draw your vectors around the angle that you have, right? Okay. Now, what I can do is, this is what we learned before. This side is opposite. This is my y, and it's opposite the 80 degrees, so I write hypotenuse sine 80. And for my x, it's adjacent to the 80 degrees, so I simply write 20 cos 80. And then in my calculator, I just crunch out those numbers. So I do sine 80 times 20, which I think comes out to 19.7. And then I do cos 80 times 20, and this comes out to about 3.5. Now look what it's telling us. 80 degrees is a pretty steep angle, isn't it? And so what this is telling us is that this particular black line is more up and downy than it is lefty-righty. It's got a lot of up and down. You have to really turn the up and down knob on your Etch-a-Sketch more and turn the other one less. And that makes sense. Okay, let's do the next one. Here I'll choose to draw this way, down, but I stop right here because it has to be 90 degrees, right there. That's a common mistake that's made. People draw this wrong and then they get all messed up. And here's something interesting that's going to happen. See if you figured this out. This side, which I'm going to call is y, it's on the y-axis, it's adjacent to the angle. So I'm going to use cos this time. This equals 40 times the cosine of 70, because now I'm adjacent to the angle, you see? In standard math, if your angle is in standard position, sine will always go with y and cos will always go with x, but in physics, our angles are often all over the place, so we have to remember it this way. Sine goes with whatever side is opposite the angle, and cos goes with whatever side is adjacent, and it might switch around on us like it has here. So I do 70, and I do cos, and I do times 40, and I get 13.7 for this guy. And then the other guy, he is opposite the angle, so he's my x. He will be 40 sine 70. And when I figure that out, 70 times sine times 40 is 37.6-ish. So this guy is a little more lefty-righty. But I want you to look carefully at this. Do you notice that when we did the math, we got 13.7? The math doesn't know what my picture looks like, and it doesn't know which way this arrow is pointing. But we can see it in our picture. And so actually, it's not 13.7, it's down. We have to add in the plus or the minus for down or for left. Minus goes with down and left, plus goes with right and up. In our first example, this was up and this was right, so they were both plus. We did it again, and look, the math didn't even catch the fact that this was down because it doesn't know, because these are magnitude calculations. So we have to look at the picture and realize that the real answer for our y here is negative 13.7 because it's pointing down. And in the next one, that same sort of thing will happen again. So let's just take that one up really quickly. We would go this way, not too far, right there. I have to have 90 degrees. And now x is adjacent to the angle, So it will be 100 times the cosine of 30, which is 0.87, right? So I think that should work out to about 87. And then over here, y is opposite the 30, so it would be 100 sine 30, which is a half, so that's 50. Now let's look for negatives. In the first case, it's left, so I have to make sure it's negative 87 because the math can't see it. And I have to make sure here that I put negative 50 because it's down. So you have to put those in. The math won't do this for you, unfortunately. You got to watch, which is why your picture is so important, and you have to be able to draw it correctly. Now I'm going to give you a worksheet to practice this until it sort of breaks your brain apart and oozes out your ear, because you have to learn this as well as you know how to add regular numbers. In grade 1 you learned that. Here we are in grade 11 learning how to add vectors, but you have to know how to do this as easily as you would add. All right.